So today we have another mixed spectroscopic techniques question where we are given information on mass spec, infrared and NMR, and we have to put those clues together like pieces of a jigsaw and work out the identity of the organic molecule. So I'm going to start with the easiest piece of spectroscopic data, which is the infrared, as you can tell a lot about the molecule just from the wave numbers you see in the spectrum. So the datasheet I will be using for today's question is attached in the description below. So if you want to use the exact numbers I am using, please download that first. With that said, let's get into it. So immediately I can see that there is a really strong sharp peak at the sort of 1700-1800 range, and that is always a C double bond O, a carbonyl. But we don't know yet whether that is an aldehyde, ketone, ester, carboxylic acid. So we need to look at the other peaks that are there as well. So fortunately we have another very good peak at, we take a look at that, it's probably around say 1300. And if you look at the data sheet, that is indicative of a C single bond O. At this point you're thinking, right, we have a C double bond O and a C single bond O, so you have to think about functional groups that have those bonds. So the obvious ones that come to mind are the carboxylic acid and the ester. But we need to do a little bit more digging before we can conclude whether it's a carboxylic acid or an ester. And what we're going to use for that is this peak. So we can see that peak is starting around, so when you do infrared, by the way, make sure you take your reading from where the peak begins to sort of grow downwards, like so. And you can see that it's sort of starting around 2800 to 3100. And if you look at the data table for that, you'll see that value is indicating a CH bond, which doesn't really tell us much because lots of organic molecules obviously contain CH bonds. So what we need to do is start eliminating common functional groups and then see what we have left. So if we put on the screen, there's the aldehyde group, there's the ketone group, there's the alcohol group, and what we can do is look at the infrared spectra for other common functional groups like the carboxylic acid, like the alcohol. By looking at those spectra, we can determine whether or not that functional group is present in the molecule. So the alcohol functional group always looks like this, which you can see has this sort of double dip. It goes down, comes back up, goes down, comes back up. And then the carboxylic acid looks like this. It kind of looks like an upside down mountain known as an inverted mountain. So immediately I can see that this molecule definitely doesn't contain a carboxylic acid, so we can cross that out, and definitely doesn't contain an alcohol because the peaks over this side do not look anything like those functional groups. So I have produced a video on this where I go through how to read infrared spectrum very quickly so that you can determine the molecule without actually reading the question, just based off the shape of the spectra. And that's attached below. So alcohols have the double dip, as it's called. Carboxylic acids have the inverted mountain. You can clearly see from the spectra those peaks are not there, so it's neither of those functional groups. So that leaves us with ester, aldehyde, ketone. Well, the infrared spectra is telling us that this molecule must contain two oxygens because we have the C double bond O and the C single bond O. So therefore, it cannot be an aldehyde and it cannot be a ketone, which leaves us with the ester functional group. So for now, that is what I'm going to go with. Obviously, we have to read the other clues we've got, but you can see how I've got to that functional group by a process of elimination. I've eliminated the things that it definitely cannot be, and I've looked to see what I have left. So the ester functional group is the first jigsaw piece, if you like. So the way to go about solving these questions is to identify the parts of the molecule. Let's think of them as jigsaw pieces. You put those jigsaw pieces down on the page, and then you assemble them at the end, and then see if your drawing of the organic molecule matches, in particular, the proton NMR spectra, which is the next thing I'm going to look at. If you look at the NMR spectra, we can see there are 5 distinct peaks. So in my NMR video, I describe the 3 basic rules for both proton and carbon NMR, which I will briefly repeat here, which is number 1, the number of peaks is equal to the number of distinct environments. Number 2, the area, which is also known as the integration. That word comes from maths, by the way. So the area integration under the peak is equal to the number of hydrogens in that environment. And then number 3, this one's a really useful one, is the greater the chemical shift, which is the delta value, that corresponds to the greater the electronegativity of the environment. So for example, if you have hydrogens that are in an environment of 2 oxygens or fluorines, for example, so attached to carbons right next to those very electronegative environments, then that drives the chemical shift upwards. If you look at the data table, it should come as no surprise that protons, so hydrogens, that are in an environment of a carboxylic acid, or maybe carbonyl group where there's halogens around, have chemical shifts of up to 11 or 12, and you'll see that on the datasheet. Whereas on the other side, between 0 and 1, the hydrogens are just on basic carbon environments, so like methyl groups, ethyl groups. Well, they're not electronegative, so they have much smaller chemical shifts. So these are the 3 rules of NMR that I'll be using to work out this molecule. We have an ester group so far, and we know that this molecule has 1, 2, 3, 4, 5 distinct environments. So my drawing at the end must have 5 distinct proton environments. Now if we go to the top of the question, let's see if we have any clues there. It says compound A has 6 carbon atoms and can be made from propene using several steps. So that's all we have. We know that it's got 6 carbons, and we know it definitely has 2 oxygens. So let's start putting this down. So if we have the C double bond O with the oxygen and then a carbon either side, you can see immediately I've already used 3 of the 6 carbons available. So that's great, because I only need to work out the other 3. So let's box that. That is our first jigsaw piece, if you like. Now what I'm going to turn to next is the NMR to help me determine what those environments are. So the first peak that jumps out at me, if I zoom in so you can see this, is this one at 4. Now this is always a really good peak to look for. First of all, it tends to occur between 3.8, 3.9 to 4.3, and it always represents the same thing, which is a hydrogen bonded to a carbon directly bonded to an oxygen. So in other words, this bit, right, where you have a hydrogen coming off of that carbon. So why is that useful? Because that is our starting point to work out what is coming off the C single bond O, oxygen, and the proton environments around that. So you can see from the peak that it's a triplet, and that the area or the integration of that environment is 2H. So what does that mean? It means in that proton environment there are 2 hydrogens, and those 2 hydrogens must be next to a carbon which also has 2 hydrogens, because it's split into a triplet. And from what is called the n+1 rule, so just assuming you know what that means, the n stands for the number of hydrogens on the adjacent carbon. To get a triplet, you must have 2 on the neighbouring carbon plus the 1 will equal 3. And that number there, that tells you what the current peak will be split into, which in this case is a triplet. So now I can start to build the molecule. So let's make this a little bit more clear. So we've got C double bond O, C single bond O, a carbon that has to have two hydrogens, and that also must be bonded to a carbon which has two hydrogens as well, because if I just circle what I mean there, that is the neighbouring environment, of which the number of hydrogens attached to that neighbouring environment is 2, and then the 2 plus 1 makes 3. So this is what causes that to split into a triplet. So far we have, that's 2H, and we know it's a triplet. And we know there's a CH2 right next to it. Now we don't know this is the final answer yet, but we're building the picture of what this molecule could look like. So let's keep going. Now the other one that looks very interesting is this idea of a multiplet. So when I'm doing these NMR questions, I always start with this peak and then anything that's like distinct and very interesting, like a multiplet. So if we zoom in, really zoom in there, let's grab a different color for this. Hopefully you can see. And by the way, when you look at these environments in your exam question, whatever it is that you're doing, you must count every single split, every single little bit you can see, because it does matter. So if you look at this very closely, let me just hold it there so you can see that. We have 1, 2, 3, 4, 5, 6. So that peak is split into 6. So there's 6 splits. So that's the multiplet. So if it's split into 6, if we work backwards from that, n plus 1 is equal to 6, which means the number of hydrogens on the neighbouring environment to cause that must be 5. So now we have to get a carbon environment where the hydrogens in that environment are adjacent to 2 other environments that have a total of 5 hydrogens to get that multiplet. And also we have a chemical shift for that multiplet at about 1.6, I would say, 1.7. So looking at my data table for the NMR, I can see that 1.6 to 1.7 indicates a classic carbon bonded to the hydrogen environment, indicates a hydrogen bonded to a carbon, which is then directly attached to another carbon. So in other words, a normal alkyl group. So if you're using the data table I am, you'll see it's called RCH. So it has to be in an alkyl chain somewhere. If we go back down to our drawing, what I can try here is I can add another carbon to this carbon here. And well, I know there's 2 hydrogens there. So if I finish this with a CH3, that last environment here has 3 hydrogens. So this one in the middle, you can see on the left it's next to 2 hydrogens. On the right it's next to 3 hydrogens. So therefore, according to the n plus 1 rule, that'll be 5 plus 1 makes 6. So that middle carbon, that middle CH2 group rather, must be the multiplet. And it fits perfectly, look, because there's an alkyl group that way and an alkyl group that way, as in the CH2 to the left and the CH3 to the right. Alkyl group, by the way, if you're wondering, just a quick recap, is something, just a CH3, a C2H5, any carbon chain basically. And then finally, this has created a CH3 in the end. So this must have an integration of 3H. And if you look at this environment, that is next to a CH2. So N will be 2. 2 plus 1 will make 3. So therefore this will be a triplet. So let's go back to our NMR spectra. Do we have a triplet which has an integration of 3H, which is in the alkyl region? And actually we have 2. We got one there and we have another one there. So this is looking good. So it could be either one of those because the range fits. It's an alkyl CH3. It's next to a CH2 to create the triplets. So it could be either one of them. Now I don't know which one yet, but it might be one of them. So far we have deduced either one of those 2. We've done this one. We've determined this one. And now we have this quartet. So a quartet which has 2 hydrogens in it. Now, how is that possible? How can we create a quartet with two hydrogens in it? Well, usually when I see this, not just for this example, but for many organic molecules, when you have a quartet, it's usually because it is next to a CH3. So the classic is this, the ethyl group, which I'm just drawing on the left here. And you'll see with this, it works very well, because if I just circle the bits that are relevant, this here, you can see to the left is next to a CH3. So that would make a quartet. It's called a Q. And then the CH3, which I'll just circle in blue here, that is immediately next to a CH2. So that would make, so this environment would be a triplet. So that's what I'm thinking about in my mind here. Maybe one of these triplets and quartets belong together as a CH2-CH3 ethyl group. So how can I confirm if this is correct? Well, this is where the chemical shift comes in. And if I just highlight a bit there in pink, you can see that it starts at around 2.2 and then finishes at around 2.4. We zoom in. So yeah, 2.2 finishes at about 2.4. And if I go to my datasheet, the options between a chemical shift of 2 to 3 are a benzene ring with a CH group on, so it's definitely not going to be that. A carbon with a hydrogen attached, which is bonded to a nitrogen. Well, there's no mention of nitrogen in the starting paragraph. It's just a hydrocarbon with some oxygen, so it's definitely not that. And then the bottom one is a C double bond O bonded to a carbon with a hydrogen. Well, we definitely have that functional group, so therefore it must be that functional group, as in the table it's quoted as this. There's a C double bond O, like that. So it's this hydrogen it's referring to that has a chemical shift of about 2.2. So if we go to our drawing, look at the parts we have so far. Look at the jigsaw pieces that we have so far. The only thing we haven't done any work on is the N carbon there. And this is the bit that's missing. So maybe that belongs to the left-hand side of the C double bond O. So let's give it a go. So if I put that in there, that will give a CH2 and a CH3. And if I just circle my drawing, I can see that would be a quartet because it's next to a CH3 on the left. And this one would be a triplet because it's next to a CH2 to its right. So now we have a molecule which has been made up of these individual parts, these jigsaw pieces, if you like. And we can see from my drawing that it does indeed have 6 carbons. So C6, the hydrogens, there's 12 hydrogens, and there's 2 oxygens. So let's draw this more clearly because I'm not quite sure if this is correct yet. So to determine whether your molecule is likely to be correct or not, let's make another clearer sketch of it. And then the best way to prove this is to circle the environments in your drawing. And then once you have done that, match those environments with those in the proton NMR. And if those environments from the proton NMR match exactly the environments in your molecule in terms of integration, in terms of splitting, then you know for a fact you've done it right. And this is the quickest way to full marks in these styles of question because, as you know, they can be sort of 8 or 10 markers. And the way to get the answer or explain it the most clearly is to draw your molecule, circle each environment, which I'm doing right now, label each environment with your own labels, and then put those labels on the supplied proton or carbon NMR that you've been given. So let's call this A, B, C, D, E. And the reason why that's so important is because even if you mess up the explanation and you're not very good with, structuring sentences in English, which is what I'm like, I like science, not English. The examiner can see that you have determined the structure of this molecule without cheating, without getting lucky. You've proved beyond reasonable doubt that you've absolutely nailed it. And then even if your explanation is subpar, if you've got your drawing and your labels, you're going to get full marks. So let's take a look to see whether these environments on my molecule match those of the NMR. So I'm just going to clean up the graph before we start. So I'm going to start with the first environment I identified, which is the one at around a chemical shift of 4. And that environment is C, which indicates a hydrogen bonded to a carbon directly bonded to an oxygen. So if I just grab a different colour to show that, it's that one there. And that must be between around 3.8 to 4.3. And you can see that my drawing fits that environment perfectly. The integration is 2H. It is next to a CH2 on the right, which means it must be a triplet. So that condition and that condition are both met. Then the next one, which is actually quite easy to spot, is the multiplet. So that would be environment D, because you can see that has an integration of 2H, so 2 hydrogens in that environment, and is split into 6. Let's call it 6. Because there's 2 hydrogens on the left in the CH2, and then there's 3 hydrogens on the right, which is environment E. So that's where the multiplet 6 comes from. So that one must be D. Next is the CH2 attached to the C double bond O. So that has an integration of 2H and has to have a shift around or between 2 and 2.5. So therefore the only one that fits that is this one, B. So finally then we need to decide which triplet, A or E, belongs to the peaks we have at, I think that one's 1.2 and that one's about 0.8. How do we know which is which? So for that, I'm going to employ rule number 3, which is the greater the chemical shift, the greater the electronegativity of the environment. So this is how we work this one out. So you can see environment A is closer to the C double bond O because it's only one CH2 away. So if we think we're going this way, whereas environment E, you can see that it's a lot further away from the C double bond O, C single bond O, because there's a CH2 there and another one there. So therefore, I can make an educated guess and say that environment A is the more electronegative environment compared to environment E. So therefore, A will be this one and E will be this one. Lastly, we can take a look at the mass spectrum. And by far the most important peak from a mass spectra is the last one, which tells us the mass of the molecule, which according to this is 116. So the name for this peak, by the way, is called the molecular ion peak, and it tells us, as I said, the overall mass of the molecule. So according to this is 116. And if you look at my molecule, let's do a quick check. So we have 15 for the CH3, 14 for the CH2, 28 for the C double bond O, 16 for the oxygen, 14 for another CH2, 14 for another CH2, and then 15 for the end, CH3. All of that adds up to 116. So that is very reassuring because the molecule that I've just made up fits that number perfectly. So to summarize, what have I done today? You look at the 3 clues that are usually given to you, which are infrared, mass spec, and NMR. You treat each of those clues as like pieces of a jigsaw. So you pick off the functional groups that are present from the infrared, and by a process of elimination, which is this method here, you work out what functional group or functional groups may be present. And you just put them down on the page like a piece of a jigsaw. Then the next thing you go to is your NMR, and you work out how many distinct chemical environments there are. And then by looking at the NMR spectra datasheet, you can determine individually what each of those environments would look like. So for example, I was drawn to this one, which in the datasheet is OCH. And you can see there we have another piece of the jigsaw. And then what you do at the end, as well as looking at the mass spec or maybe some other clues you're given, like they might give you a result of a chemical test. So they might say decolorizes bromine water and you think, oh, okay, it contains a double bond, or a tolerance test or failings or something like that. Once you put all of those clues together, put the functional groups down on the page, like I did there, as pieces of a jigsaw, and then assemble them in a way that each environment in your drawing, so the ones that I've circled here, like so, match the environments of the proton NMR. And I will say this, for really difficult questions, there may be a certain amount of trial and error involved. And that's okay. Put the pieces together, make sure they add up, like this here, that they actually come to the final RFM. And then once you're happy with your drawing, circle the environments, match them to the NMR, and then you'll know then whether you got it correct or not. That's it for today. Please check out the other videos I've produced on this topic. I think it's really hard, but once you've had enough practice, you will get a lot better at being able to spot what these molecules are. The links for those other lessons are in the description below. Like and subscribe, it helps the channel. And thank you for watching.